Hello there. Look up at the night sky, and if you're patient, if you wait long enough for your eyes to adjust to the darkness, you might see it. Our moon, silent, pale, tracing its ancient path across the vault of stars. It has been there every night of your life, every night of every human life that has ever been lived. Before cities, before language, before we were even recognizably human, the moon was there, pulling at the oceans, lighting the darkness, keeping watch. Across the solar system, dozens of worlds orbit not the sun but other planets. Moons of ice and rock, moons with buried oceans and active volcanoes, moons captured from the asteroid belt, and moons born in the violent collisions of the early solar system. Some are larger than planets. Some are barely more than tumbling boulders. Each one is a world unto itself, with its own geology, its own history, its own quiet mysteries. Tonight, we are going to explore the most relaxing facts about moons. Not just our moon, though we will spend time with that familiar companion, but the strange and beautiful moons of Jupiter and Saturn, the small, captured asteroids of Mars, the distant and frozen moons of the outer planets, and even the theoretical exomoons that might orbit planets around other stars. We will move slowly through these facts, letting each one settle, giving you time to imagine these distant worlds as they orbit in the darkness. So settle in. Dim the lights. Let your breathing slow. We have a long journey ahead through the quiet places of the solar system, where moons drift in their orbits, patient and eternal. Our moon was born in catastrophe, about 4.5 billion years ago, when the Earth was still young and molten. A Mars-sized planet called Theia collided with our world. The impact was so violent that it vaporized rock, sending a massive plume of debris into orbit around the Earth. This debris, a ring of molten rock and vapor, gradually coalesced under its own gravity, cooling and solidifying into the moon we see today. This giant impact hypothesis explains why the moon's composition is so similar to Earth's mantle, why it lacks a substantial iron core, and why it's so large relative to its parent planet. The collision that created the moon also tilted Earth's axis, giving us our seasons, and sped up Earth's rotation, making days much shorter than they are now. From violence came our constant companion, and from that companion came stability, the regular rhythm of tides and seasons that may have been crucial for the development of life. Every year, the moon moves approximately 3.8 centimeters farther from Earth. This gradual recession is caused by tidal forces. The moon's gravity pulls on Earth's oceans, creating tides, but Earth's rotation drags those tidal bulges slightly ahead of the moon. The gravitational pull of these bulges accelerates the moon in its orbit, causing it to slowly spiral outward. At the same time, this tidal interaction is slowing Earth's rotation, making our days incrementally longer. Billions of years ago, when the moon was much closer, days were only about 5 hours long, and the moon loomed enormous in the sky, raising tides hundreds of meters high. Billions of years in the future, if the sun doesn't engulf both worlds first, the moon will be so distant that it will appear much smaller, and Earth's day will be much longer. The moon is not fixed in place. It's slowly leaving us, though the process is so gradual that countless human generations will live and die without noticing any change. The moon always shows us the same face. This is not coincidence, but the result of tidal locking, a gravitational phenomenon where an orbiting body's rotation period matches its orbital period. Early in the moon's history, when it was closer to Earth, and still geologically active, Earth's gravity created tidal bulges in the moon's rocky body. These bulges created friction, gradually slowing the moon's rotation until it became synchronized with its orbit. Now, one lunar day equals one lunar orbit, about 29.5 Earth days. This means there's a far side of the moon that remained hidden from human eyes until 1959, when the Soviet Luna 3 spacecraft photographed it. The far side looks different from the near side. It has fewer of the dark volcanic plains called Maria, and is more heavily cratered. This asymmetry might be due to the moon's slightly offset center of mass, or differences in crustal thickness. The far side is not dark. It receives just as much sunlight as the near side, but it is forever turned away from Earth, a hemisphere of the moon that no human saw until we developed spaceflight. The moon has an atmosphere, but calling it that is generous. It's technically an exosphere, so tenuous that it's essentially a vacuum. The total mass of the lunar atmosphere is about 25,000 kilograms, less than the mass of a single large truck. For comparison, Earth's atmosphere has a mass of about 5 quadrillion kilograms. The moon's exosphere is constantly being replenished and lost. The moon is not geologically dead. It experiences moonquakes, tremors caused by tidal stresses from Earth's gravity, thermal expansion and contraction as the surface heats and cools, and the gradual cooling and contraction of the lunar interior. Seismometers left by Apollo astronauts detected thousands of moonquakes over several years. Most are very weak, far weaker than earthquakes, but some shallow moonquakes can reach magnitudes of around 5 on the Richter scale. These quakes can last for over 10 minutes, much longer than earthquakes, because the moon's dry, rigid interior doesn't dampen seismic waves the way Earth's water-saturated crust does. The moon is slowly shrinking as its interior cools, contracting by about 50 meters in radius over the past few 100 million years. This contraction creates thrust faults, cliffs where one section of crust has been pushed up over another. These scarps, some over a kilometer high, are evidence that the moon is still, very slowly, geologically active. The moon once had a magnetic field, generated by a dynamo in its molten iron core. Rocks brought back by Apollo astronauts show remnant magnetization, evidence that they formed in the presence of a strong magnetic field, perhaps as strong as Earth's field today. This lunar dynamo operated between about 4.2 and 3.5 billion years ago, then weakened and eventually ceased as the moon's core cooled and solidified. Why the moon had such a strong magnetic field, given its small size, remains a mystery. Some researchers propose that the moon's core was stirred by the gravitational effects of Earth when the moon was closer, creating the convection necessary for a dynamo. Others suggest that the giant impact that formed the moon left the core in a highly energetic state. Whatever the cause, the lunar magnetic field is long gone. Today, the moon has only weak, localized magnetic fields associated with certain impact basins, possibly created when magnetized impactors struck the surface, or when impact-generated plasma interacted with an existing field. For decades, scientists believed the moon was bone dry. Then in the 1990s, spacecraft detected signs of water ice in permanently shadowed craters near the lunar poles. These craters, located in regions where the sun never shines, are among the coldest places in the solar system, with temperatures around 40 Kelvin, cold enough to trap water ice for billions of years. The ice likely comes from multiple sources: comets and asteroids that impacted the moon, solar wind hydrogen that combined with oxygen in lunar minerals, and possibly water released from the moon's interior during ancient volcanic eruptions. The amount of ice is uncertain, but some estimates suggest millions of tons. This ice is not pure. It's mixed with lunar soil, creating a kind of frozen regolith. For future lunar explorers, this ice represents a crucial resource, potentially providing drinking water, oxygen for breathing, and hydrogen and oxygen for rocket fuel. The permanently shadowed craters are time capsules, preserving not just water, but a record of volatile delivery to the inner solar system over billions of years. The moon's surface is covered in regolith, a layer of loose, fragmented material created by billions of years of meteorite impacts. This regolith ranges from fine dust to boulder-sized rocks and averages about 4 to 5 meters deep in the Maria and 10 to 15 meters deep in the highlands. It's not soil in the biological sense. There's no organic matter, no life, just pulverized rock and glass. The regolith has unique properties. It's extremely abrasive, damaging equipment and spacesuits. It's electrostatically charged by solar radiation, causing it to cling to everything. It's also an excellent insulator, which is why temperatures just below the surface remain relatively constant despite the extreme temperature swings at the surface. The regolith contains a record of the sun's history, as solar wind particles have been implanted in the grains for billions of years. It also contains tiny glass beads, created when meteorite impacts melted rock, which then cooled rapidly into spheres. Walking on the moon, astronauts described the regolith as having a consistency somewhere between sand and talcum powder, and it compressed under their boots, leaving those famous footprints. The moon is the primary driver of Earth's tides, though the sun also contributes. The moon's gravity pulls on Earth's oceans, creating a bulge of water on the side facing the moon, and, less intuitively, on the opposite side as well. This opposite bulge exists because the moon is pulling Earth itself away from the water on the far side. As Earth rotates beneath these bulges, we experience high and low tides. When the sun, moon, and Earth align during new and full moons, their gravitational effects combine, creating spring tides with the highest highs and lowest lows. When the sun and moon are at right angles during quarter moons, their effects partially cancel, creating neap tides with smaller tidal ranges. Tides don't just affect oceans. The moon also raises tides in Earth's crust, though these are much smaller, only about 30 centimeters. Over geological time, tides have had profound effects, slowing Earth's rotation, stabilizing our axial tilt, and possibly creating tidal pools that served as crucibles for early life. The dark patches on the moon, visible to the naked eye and imagined by various cultures as a face, a rabbit, or other figures, are called Maria, Latin for seas. Early astronomers thought they were bodies of water, but they're actually vast plains of solidified lava between about 3.9 and 3.1 billion years ago. During a period of intense bombardment, massive asteroids struck the moon, creating enormous impact basins. Magma from the moon's interior welled up through the fractured crust, flooding these basins with lava that cooled into the smooth, dark basaltic rock we see today. The Maria are darker than the surrounding highlands because basalt reflects less light than the anorthosite that makes up the highlands. The Maria are also younger and therefore less cratered. Most Maria are on the near side of the moon, possibly because the crust is thinner there, making it easier for magma to reach the surface. These frozen lava seas are a record of the moon's volcanic past, a time when the lunar interior was hot enough to produce massive lava flows. The moon stabilizes Earth's axial tilt, and this stability has been crucial for the development of complex life. Earth's axis is tilted about 23.5 degrees relative to its orbital plane, and this tilt gives us our seasons. Without the moon, gravitational perturbations from other planets, particularly Jupiter, would cause Earth's axial tilt to vary chaotically over millions of years, swinging from nearly 0 degrees to 85 degrees or more. Such dramatic changes would create extreme climate instability, with the poles sometimes pointing nearly at the sun and sometimes away, causing wild swings in temperature and making it difficult for complex ecosystems to evolve. The moon's gravity acts like a gyroscopic stabilizer, keeping Earth's tilt relatively constant, varying only about 2.4 degrees over a 41,000-year cycle. This stability has allowed Earth to maintain relatively stable climate zones, temperate regions, polar ice caps, and tropical zones that have persisted long enough for life to adapt and diversify. We owe much of our planet's habitability to the moon's steadying presence. Scattered across the moon's surface are strange, bright markings called lunar swirls. These sinuous, high-albedo features look like someone took a paintbrush to the lunar surface, creating swirling patterns of bright and dark material. The most famous is Rhina Gamma, but swirls exist in several locations. They're always associated with localized magnetic anomalies, regions where the lunar crust has a stronger magnetic field than surrounding areas. The leading theory is that these magnetic fields deflect the solar wind, protecting the surface from space weathering that normally darkens lunar soil. The bright swirls are areas that have been shielded, while the darker surrounding areas have been exposed to the full effects of solar wind bombardment. But how these magnetic anomalies formed remains uncertain. They might be remnants of ancient magnetized lava flows, or they might have been created when magnetized asteroids struck the surface, or they might be the result of plasma interactions during major impacts. The swirls are beautiful, mysterious, and a reminder that the moon still holds secrets. While the moon is tidally locked to Earth, always showing us the same face, we can actually see slightly more than half of the lunar surface over time, due to libration. Libration is an apparent wobbling of the moon caused by several factors. The moon's orbit is elliptical, not circular, so its orbital speed varies. When it's closer to Earth, it moves faster, and when it's farther, it moves slower. But its rotation rate remains constant. This means we can sometimes see a bit farther around the eastern or western edge, a phenomenon called longitudinal libration. The moon's axis is also tilted slightly relative to its orbital plane, allowing us to peek over the north and south poles at different times, called latitudinal libration. There's also a small daily libration, caused by viewing the moon from different positions as Earth rotates. Combined, these librations allow us to see about 59% of the lunar surface from Earth over time, though never more than 50% at once. The remaining 41% remained hidden until spacecraft photographed the far side. In January 1610, Galileo Galilei pointed his primitive telescope at Jupiter and saw something that would change humanity's understanding of the cosmos. 4 points of light arranged in a line near the giant planet, moving from night to night. These were not stars. They were moons, worlds orbiting Jupiter just as our moon orbits Earth. This discovery shattered the ancient belief that everything in the heavens revolved around Earth. Here was proof that celestial bodies could orbit something other than our world. Galileo called them the Medicean stars, hoping to carry favor with his patrons, but history remembers them as the Galilean moons, Io, Europa, Ganymede, and Callisto. These 4 worlds are among the largest moons in the solar system. Ganymede is larger than the planet Mercury. Each is a distinct world with its own character, from volcanic Io to ice-covered Europa to ancient cratered Callisto. They orbit Jupiter in a cosmic dance that has continued for billions of years, locked in gravitational resonances that shape their geology and perhaps their potential for life. Io is the most volcanically active body in the solar system, and it's not even close. Its surface is constantly being resurfaced by volcanic eruptions, with hundreds of active volcanoes spewing sulfur and sulfur dioxide hundreds of kilometers into space. Some of these eruptions are so powerful that they create umbrella-shaped plumes visible from Earth-based telescopes. The source of this intense volcanic activity is tidal heating. Io orbits deep within Jupiter's powerful gravitational field, and its orbit is slightly elliptical due to gravitational interactions with Europa and Ganymede. As Io moves closer to and farther from Jupiter, the tidal forces stretch and squeeze the Moon, generating enormous amounts of heat through friction in its interior. This heat keeps Io's interior molten and drives the volcanic activity that gives the Moon its distinctive yellow, orange, and red coloration from sulfur compounds. Io has no impact craters because its surface is so young, constantly buried under new volcanic deposits. It's a world in perpetual transformation, its surface never more than a few million years old, a tiny fraction of the age of the solar system. Europa's surface is one of the smoothest in the solar system, a shell of water ice crisscrossed with dark streaks and ridges. This ice is not static. It's the frozen surface of a global ocean that lies beneath, an ocean that may contain twice as much water as all of Earth's oceans combined. The evidence for this subsurface ocean is compelling. Europa's magnetic field behaves in a way consistent with a conducting fluid beneath the surface. The Moon's surface shows signs of ice tectonics, where blocks of ice have shifted and rotated, floating on a liquid layer below. There are few impact craters, suggesting the surface is geologically young, constantly renewed by ice welling up from below. The ocean exists because of tidal heating, the same process that makes Io volcanic. Jupiter's gravity flexes Europa's interior, generating heat that keeps the ocean liquid, despite the Moon being far from the sun. Ganymede is the largest moon in the solar system, bigger than the planet Mercury, though less massive because it's composed largely of water ice rather than rock and metal. If it orbited the Sun instead of Jupiter, we would call it a planet. Ganymede is the only moon known to have its own magnetic field, generated by a liquid iron core deep within its interior. This magnetic field creates a miniature magnetosphere around the Moon, nested within Jupiter's much larger magnetosphere. The interaction between these two magnetic fields creates auroras at Ganymede's poles, shimmering curtains of light in the Moon's tenuous atmosphere. Ganymede's surface is divided into two main terrain types: dark, heavily cratered regions that are billions of years old, and lighter, grooved terrain that appears to have been stretched and deformed by tectonic processes. Like Europa, Ganymede is believed to have a subsurface ocean, buried beneath multiple layers of ice, and possibly separated into different layers by pressure. This ocean might be sandwiched between layers of ice in different crystalline forms, a structure unlike anything on Earth. Callisto is the outermost of the Galilean moons, orbiting beyond the intense radiation belts that bombard the inner moons. Its surface is ancient, one of the most heavily cratered in the solar system, a record of 4 billion years of impacts. Unlike Io, Europa, and Ganymede, Callisto shows little sign of geological activity. Its surface is dark, composed of a mixture of ice and rock, and it lacks the bright, fresh ice that characterizes Europa and parts of Ganymede. For decades, scientists thought Callisto was a geologically dead world, a frozen relic of the early solar system. But magnetic field measurements suggest that Callisto too has a subsurface ocean, buried beneath its ancient crust. This ocean exists not because of tidal heating, which is minimal at Callisto's distance from Jupiter, but possibly because of heat from radioactive decay in the Moon's rocky interior and the insulating properties of its thick ice shell. Callisto's ocean might be very old, stable for billions of years, isolated from the surface and from the rocky interior by layers of ice. It's a quiet world, unchanged for eons, yet possibly harboring a hidden ocean in its depths. The Galilean moons are locked in an orbital resonance called the Laplace resonance, a gravitational dance where Io, Europa, and Ganymede orbit Jupiter in a precise ratio. For every orbit Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. This means that the 3 moons regularly align, and their gravitational tugs on each other reinforce in a predictable pattern. This resonance is not coincidental. It's the result of billions of years of gravitational interactions that have pushed the moons into this stable configuration. The resonance has profound effects. It maintains the orbital eccentricities of Io and Europa, preventing their orbits from becoming perfectly circular. These eccentric orbits are what create the tidal flexing that heats their interiors, driving Io's volcanism and keeping Europa's ocean liquid. Without the resonance, these moons would have circular orbits, minimal tidal heating, and very different geology. Callisto, orbiting outside the resonance, lacks significant tidal heating and is geologically quiet. The Laplace resonance is a beautiful example of celestial mechanics, a gravitational harmony that has shaped these worlds. Io orbits within Jupiter's powerful magnetosphere, and the interaction between the Moon and the magnetic field creates a phenomenon called the Io plasma torus. As Io's volcanoes erupt, they spew material into space, including sulfur and oxygen atoms. These atoms become ionized by solar radiation and by interactions with Jupiter's magnetosphere, creating a donut-shaped cloud of plasma that encircles Jupiter along Io's orbit. This torus contains about 1 ton of material and glows in ultraviolet light. The plasma in the torus is connected to Jupiter's magnetic field, and as Jupiter rotates faster than Io orbits, the magnetic field sweeps past the Moon, stripping away about 1 ton of material per second. This material spirals along magnetic field lines toward Jupiter's poles, where it contributes to Jupiter's powerful auroras. The interaction also creates a massive electrical current between Io and Jupiter, carrying about 3 million amperes of electricity. This current generates radio emissions that can be detected from Earth. Io is not just a volcanic moon, it's an active participant in Jupiter's magnetosphere, constantly feeding the giant planet's magnetic environment. Europa's surface is marked by strange features called chaos terrain, regions where the ice has been broken into blocks that have rotated and shifted before refreezing. These chaotic regions suggest that liquid water or warm, soft ice reached the surface, disrupting the solid ice shell. Some chaos regions are associated with reddish-brown material, possibly salts or organic compounds brought up from the ocean below. The exact mechanism that creates chaos terrain is debated. It might involve warm ice diapirs, plumes of less dense ice rising through the ice shell like lava lamps. It might involve pockets of liquid water trapped within the ice shell that suddenly break through to the surface. Ganymede's groove terrain is a geological puzzle. These parallel ridges and troughs cover about 40% of the Moon's surface, and they're younger and brighter than the dark cratered terrain. The grooves appear to have formed when the icy crust was stretched and fractured, possibly due to tidal heating or to the expansion of the moon as its interior differentiated, with heavier materials sinking and lighter materials rising. Some grooves are hundreds of kilometers long and several kilometers wide. They often cut across older features, indicating multiple episodes of tectonic activity. The formation of grooved terrain might have been driven by a period of intense tidal heating early in Ganymede's history, when the moon was in a different orbital configuration. Or it might be related to the freezing and expansion of Ganymede's subsurface ocean, which would cause the ice shell to crack and deform. The grooved terrain is evidence that Ganymede, despite its current geological quietness, was once a very active world, with processes that reshaped large portions of its surface. Callisto's most prominent feature is Valhalla, one of the largest impact structures in the solar system. Valhalla consists of a bright central region about 600 kilometers across, surrounded by concentric rings that extend outward for nearly 2,000 kilometers. These rings are thought to be fractures in the ice created by the massive impact that formed the basin. The impact occurred billions of years ago, and the structure has been preserved because Callisto's ice is so cold and rigid that it doesn't flow and erase impact features the way warmer ice might. Valhalla is a palimpsest, a ghost of an ancient impact, its central basin filled in by slow, viscous relaxation of the ice over geological time. The Galilean moons are bathed in intense radiation from Jupiter's magnetosphere, particularly the inner moons Io and Europa. This radiation consists of high-energy electrons and ions trapped in Jupiter's magnetic field, spiraling along field lines and bombarding the moon's surfaces. The radiation is so intense that it would be lethal to humans, delivering a fatal dose in a matter of hours on Europa, and even faster on Io. This radiation has profound effects on the moon's surfaces. It breaks apart water ice molecules, creating oxygen that forms a tenuous atmosphere. It darkens and reddens surface materials through a process called radiolysis. On Europa, it might even create oxidants that could sink into the ocean, potentially providing chemical energy for life. The radiation also poses challenges for spacecraft. Any mission to Europa must be heavily shielded, and its operational lifetime is limited by radiation damage to electronics. Ganymede, with its own magnetic field, is partially protected from Jupiter's radiation. Callisto, orbiting outside the most intense radiation belts, receives much less radiation and is considered a safer destination for future human missions. The discovery of the Galilean moons had profound implications beyond astronomy. It provided crucial evidence for the Copernican model of the solar system, where planets orbit the Sun rather than everything orbiting Earth. If moons could orbit Jupiter, then perhaps Earth was not the center of all motion. Galileo's observations were controversial, challenging the geocentric worldview endorsed by the Church. But the evidence was undeniable. Anyone with a telescope could see the moons moving around Jupiter, their positions changing from night to night in a pattern consistent with orbital motion. The Galilean moons became a symbol of the new astronomy, of observation and evidence over ancient authority. They showed that the heavens were not perfect and unchanging, but dynamic and governed by the same physical laws as Earth. These four moons, discovered more than 4 centuries ago, continue to fascinate us. They're not just points of light, but worlds, each with its own story, its own mysteries, and perhaps, in the case of Europa and Ganymede, its own hidden oceans where life might exist. Titan is the second largest moon in the solar system, the only moon with a substantial atmosphere, and one of the most Earth-like worlds we've discovered, despite being nearly 1 billion miles from the Sun. Beneath Titan's thick atmosphere and icy crust lies another ocean, this one made of liquid water, mixed with ammonia. This subsurface ocean exists because of heat from radioactive decay in Titan's rocky core, and possibly from tidal heating, though Titan's tidal heating is much less intense than Europa's. The ocean is buried beneath an ice shell perhaps 50 to 100 kilometers thick. Evidence for this ocean comes from measurements of Titan's shape and gravitational field, which suggest that the moon's interior is not rigid, but contains a layer of liquid. The ocean might be in contact with Titan's rocky core, where chemical reactions could provide energy for life. But this ocean is very different from Europa's. The presence of ammonia, which acts as antifreeze, means the ocean is likely very cold and very alkaline, creating a chemical environment unlike anything on Earth. Enceladus is a small moon, only about 500 kilometers in diameter, but it has captured the imagination of scientists searching for life beyond Earth. In 2005, the Cassini spacecraft discovered something extraordinary: plumes of water vapor and ice particles erupting from fractures near Enceladus's south pole. These fractures, nicknamed tiger stripes, are warmer than the surrounding terrain, and they're the source of geysers that shoot material hundreds of kilometers into space. Some of this material escapes Enceladus entirely, feeding Saturn's E-ring, a faint ring of tiny ice particles that extends far beyond the main rings. The plumes contain water vapor, ice particles, salts, silica, and organic molecules. The composition of the plumes indicates that they originate from a subsurface ocean in contact with a rocky seafloor. Hydrothermal activity, similar to the deep-sea vents on Earth, might be occurring on Enceladus's ocean floor. This small icy moon is actively venting its ocean into space, providing scientists with samples of a potentially habitable environment without even needing to land on the surface. Enceladus's ocean exists because of tidal heating, but the source of this heating is somewhat mysterious. Enceladus orbits Saturn in a 2-1 resonance with the larger moon Dione, meaning Enceladus completes 2 orbits for every 1 orbit of Dione. This resonance maintains Enceladus's orbital eccentricity, causing tidal flexing as the moon moves closer to and farther from Saturn. But calculations suggest that this tidal heating alone shouldn't be enough to maintain a liquid ocean and power the observed geological activity. There must be additional heat sources or mechanisms that make the tidal heating more efficient than models predict. One possibility is that the ocean is in contact with a porous rocky core, allowing for more efficient heat transfer. Another is that the ice shell is thin in some regions, allowing heat to escape more easily and creating a feedback loop that maintains geological activity. Whatever the mechanism, Enceladus is far more active than a moon of its size should be, a reminder that our understanding of planetary science still has gaps. Mimas is a small moon, about 400 kilometers in diameter, best known for the enormous impact crater Herschel that dominates one hemisphere. This crater is about 130 kilometers across, roughly 1/3 the diameter of the moon itself. The impact that created Herschel nearly shattered Mimas. Fractures on the opposite side of the moon might be evidence of shock waves from the impact propagating through the moon's interior. The crater has a central peak nearly 6 kilometers high, created when the floor of the crater rebounded after the impact. Mimas looks remarkably like the Death Star from Star Wars, though the resemblance is purely coincidental. The movie was released before high-resolution images of Mimas were obtained. Despite its dramatic appearance, Mimas was long thought to be geologically dead, a cold, inert ball of ice. But recent measurements of Mimas's rotation suggest that it might have a subsurface ocean, though this finding is controversial and requires confirmation. If Mimas does have an ocean, it would be a surprise, as the Moon shows no surface evidence of geological activity. Iapetus is one of the strangest moons in the solar system. It has a two-toned appearance, with one hemisphere bright and icy and the other dark as coal. This stark contrast is visible even through small telescopes, and puzzled astronomers for centuries. The dark material, concentrated on the leading hemisphere, the side that faces forward, as Iapetus orbits Saturn, is thought to originate from outside Iapetus itself. The leading hypothesis is that the dark material comes from other moons, particularly Phoebe, a distant dark moon that orbits in the opposite direction. Dust from Phoebe spirals inward and is swept up by Iapetus's leading hemisphere. Once deposited, this dark material absorbs sunlight, warming the ice beneath and causing it to sublimate. The water vapor migrates to colder regions, leaving behind a lag deposit of dark, non-ice material. This process creates a feedback loop, making the dark regions darker and the bright regions brighter. Iapetus also has a massive equatorial ridge, a mountain range that circles most of the Moon's equator, rising up to 20 kilometers high. The origin of this ridge is unknown, though it might be related to ancient tectonic activity or to material that fell back onto Iapetus from a destroyed ring. Tethys, Dione, and Rhea are mid-sized icy moons, each with its own character. Tethys has a massive impact crater called Odysseus, about 400 kilometers across, nearly 2/5 the diameter of the Moon. Like Herschel on Mimas, this crater is evidence of a catastrophic impact that nearly destroyed the Moon. Tethys also has a vast canyon system called Ithaca Chasma, stretching about 2,000 kilometers, roughly 3/4 of the Moon's circumference. This canyon might have formed when Tethys's interior froze and expanded, cracking the surface. Dione has bright, wispy streaks on its trailing hemisphere, which turned out to be ice cliffs, evidence of past tectonic activity. Dione might also have a subsurface ocean, suggested by measurements of its gravitational field. Rhea is the second largest of Saturn's moons and has a heavily cratered surface, indicating great age. It might have had a tenuous ring system in the past, though this is debated. These moons are not as dramatic as Titan or Enceladus, but they're worlds with their own histories, shaped by impacts, tectonics, and the slow evolution of ice over billions of years. Hyperion is a chaotic moon, both in its appearance and its rotation. It's irregularly shaped, looking like a sponge or a piece of pumice, with a surface covered in deep, sharp-edged craters. The Moon's low density suggests it's highly porous, more empty space than solid material. This porosity means that impacts don't create typical bowl-shaped craters. Instead, they excavate material without compressing it, creating the strange sponge-like appearance. Hyperion's rotation is chaotic, meaning it tumbles unpredictably rather than rotating smoothly around a single axis. This chaotic rotation is caused by Hyperion's irregular shape and its gravitational interactions with Titan. Small changes in Hyperion's orientation during close approaches to Titan lead to large, unpredictable changes in its rotation over time. If you were standing on Hyperion, the Sun and Saturn would appear to move across the sky in complex, ever-changing patterns. Hyperion is a reminder that not all moons are spherical, tidally locked worlds. Some are irregular, chaotic, and strange. Saturn's small inner moons, including Pan, Daphnis, Atlas, Prometheus, and Pandora, are shepherd moons and ring moons, small bodies that orbit within or near Saturn's ring system. Pan orbits within the Encke gap in Saturn's A ring, and its gravity clears a path through the ring material, creating the gap. Pan has a distinctive shape with a bulging equatorial ridge that makes it look like a flying saucer or a walnut. This ridge is thought to be made of ring particles that have accreted onto the moon's equator. Daphnis, even smaller than Pan, orbits in the Keeler gap and creates wave-like patterns in the gap edges as it passes. Atlas orbits just outside the A-ring and also has an equatorial ridge. Prometheus and Pandora are shepherd moons for the F-ring, a narrow, braided ring. Their gravitational interactions with the ring create kinks, braids, and clumps in the ring material. These tiny moons are intimately connected to Saturn's rings, both shaping the rings and being shaped by them, accreting ring material and clearing gaps through gravitational interactions. Phoebe is an irregular moon, meaning it has an irregular shape and an orbit that's inclined and eccentric. It orbits Saturn in the opposite direction from most of Saturn's moons, a retrograde orbit that suggests it's a captured object, an asteroid or Kuiper belt object that was gravitationally captured by Saturn. Phoebe is dark, with a surface composition that includes water ice, carbon dioxide, and organic compounds. Its density suggests it has a rocky core, unlike Saturn's larger icy moons, which are mostly ice. Phoebe is thought to be a remnant from the outer solar system, a primitive body that formed in the region beyond Neptune and was later captured by Saturn. Studying Phoebe provides insights into the composition of objects in the Kuiper belt, that distant region of icy bodies beyond Neptune's orbit. Phoebe is also the source of Saturn's largest ring, the Phoebe ring, a vast, tenuous ring of dust particles that extends millions of kilometers from Saturn. This ring was discovered in 2009 by the Spitzer Space Telescope and is fed by micrometeorite impacts on Phoebe that kick up dust particles. Saturn has over 80 known moons, and many of the smaller ones are likely captured asteroids or fragments from larger moons that were shattered by impacts. These irregular moons orbit in groups with similar orbital characteristics, suggesting they share a common origin. For example, the Norse group consists of several moons with similar retrograde orbits, possibly fragments of a single larger moon that was destroyed. The Inuit group and the Gallic group are other examples. These small moons are difficult to study because they're so faint and distant, but they provide clues about the history of the Saturn system, about capture events and collisions that occurred over billions of years. The relationship between Saturn's moons and rings is complex and dynamic. The rings are not static. They're constantly evolving, shaped by gravitational interactions with moons, by collisions between ring particles, and by the slow inward spiral of material towards Saturn. Some moons orbit within the rings, like Pan and Daphnis, clearing gaps and creating waves. Other moons orbit just outside the rings and act as shepherds, confining the ring material through gravitational interactions. Material from the rings can accrete onto moons, and material from moons can be ejected into the rings by impacts. Enceladus feeds the E-ring with its plumes. Phoebe feeds the Phoebe ring with dust from micrometeorite impacts. The rings themselves might be relatively young, perhaps only a few 100 million years old, possibly created when a moon or comet wandered too close to Saturn and was torn apart by tidal forces. The moons and rings are not separate systems, but parts of an interconnected whole, constantly interacting and evolving. Titan's thick atmosphere has hidden its surface from optical observation, but radar and infrared instruments on the Cassini spacecraft and the Huygens probe that landed on Titan in 2005 revealed a world of remarkable diversity. There are vast dune fields near the equator, made not of sand, but of organic particles that have settled from the atmosphere. These dunes are hundreds of kilometers long and shaped by winds that blow predominantly from east to west. There are mountain ranges, possibly made of water ice, which is as hard as rock at Titan's frigid temperatures. There are impact craters, though fewer than expected, suggesting that Titan's surface is geologically young, constantly resurfaced by processes like dune migration, methane rain erosion, and possibly cryovolcanism. And there are the lakes and seas, concentrated near the poles, filled with liquid methane and ethane. The largest, Kraken Mare, is larger than the Caspian Sea on Earth. Titan is a world where you could stand on solid ground, look up at a hazy orange sky, and watch methane rain fall into a methane sea. It's alien, yet hauntingly familiar. Uranus has 27 known moons, all named after characters from the works of William Shakespeare and Alexander Pope, a unique naming convention among planetary moons. The 5 largest, Miranda, Ariel, Umbriel, Titania, and Oberon, were all discovered before the space age through telescopic observations. These moons are icy worlds, composed of roughly equal parts rock and ice, orbiting a planet that itself is unusual. Uranus is tilted on its side, with its axis of rotation nearly in the plane of its orbit, and its moons orbit in the same tilted plane, circling the planet's equator. This extreme tilt means that Uranus and its moons experience extreme seasons. For about 42 years, one pole faces the sun while the other is in darkness. Then the situation reverses. The moons were largely mysterious until 1986, when Voyager 2 flew past Uranus, providing our only close-up views of these distant worlds. Miranda is the smallest and innermost of Uranus's 5 major moons, but it has one of the most bizarre and varied surfaces in the solar system. Its landscape is a patchwork of different terrain types, as if the moon were assembled from mismatched pieces. There are old, heavily cratered regions, and there are younger regions with parallel ridges and grooves called coronae. The most dramatic feature is Verona Rupes, a cliff that drops about 20 kilometers, making it one of the tallest cliffs in the solar system. If you jumped off this cliff on Miranda, where gravity is only about 1/100th of Earth's, you would fall for about 10 minutes before hitting the bottom. The origin of Miranda's chaotic terrain is debated. One hypothesis is that Miranda was shattered by a massive impact and then reassembled, with the pieces coming together in a jumbled configuration. Another is that the different terrain types formed through tidal heating when Miranda was in an orbital resonance with other moons, causing its interior to partially melt and drive geological activity that resurfaced parts of the moon. Ariel and Umbriel are similar in size, both about 1,200 kilometers in diameter, but their surfaces are strikingly different. Ariel has a relatively bright surface, with extensive evidence of past geological activity. It has long, branching valleys, possibly graben where the crust has been stretched and dropped between parallel faults. It has smooth plains that might be areas where viscous ice flows or cryovolcanic eruptions resurfaced the terrain. The presence of these features suggests that Ariel was geologically active in the past, possibly due to tidal heating. Umbriel, in contrast, is dark and heavily cratered, with little evidence of geological activity. Its surface is ancient, largely unchanged for billions of years. The reason for this difference is unclear. Both moons are similar in size and composition, and they orbit at similar distances from Uranus. Yet one shows evidence of a dynamic past, and the other appears to have been geologically dead for most of its history. Umbriel's most notable feature is a bright ring on its surface called Wunda, possibly the floor of a large impact crater. Titania and Oberon are the largest of Uranus's moons, each about 1,600 kilometers in diameter. Titania has a surface marked by large fault valleys, evidence that the Moon's crust has been stretched and fractured. These valleys can be hundreds of kilometers long and several kilometers deep. The presence of these features suggests that Titania's interior froze and expanded, cracking the surface. There are also relatively few large craters, suggesting that some resurfacing has occurred, possibly through cryovolcanism or viscous relaxation of the ice. Oberon's surface is heavily cratered, indicating great age. But it also has some unusual features. Some craters have dark material on their floors, possibly a mixture of ice and carbonaceous material that was excavated from the Moon's interior by the impacts. Oberon also has a large mountain, about 6 kilometers high, visible on the limb in Voyager images. Both Titania and Oberon are cold, distant worlds, but they show evidence of complex geological histories, of processes that shaped their surfaces billions of years ago. Uranus's smaller moons include a group of inner moons that orbit between the planet and Miranda. These moons, including Puck, Cordelia, Ophelia, Bianca, Cressida, Desdemona, Juliet, Portia, Rosalind, and Belinda, are small, irregularly shaped, and dark. They were mostly discovered by Voyager 2, though some have been found in more recent observations. Some of these moons are shepherd moons for Uranus's narrow rings, similar to the shepherd moons of Saturn. Cordelia and Ophelia, for example, orbit on either side of Uranus's epsilon ring, confining the ring particles through their gravitational influence. These small moons are likely fragments from larger moons that were shattered by impacts, or they might be captured objects. They're difficult to study because they're so small and distant, but they're part of the Uranian system, orbiting in the planet's tilted equatorial plane, experiencing the same extreme seasons as the larger moons. Neptune has 14 known moons, dominated by Triton, one of the most fascinating moons in the solar system. Triton is large, about 2,700 kilometers in diameter, making it the 7th largest moon in the solar system. But what makes Triton truly unusual is its orbit. It orbits Neptune in a retrograde direction, opposite to the planet's rotation, and opposite to the orbits of Neptune's other moons. This retrograde orbit is strong evidence that Triton is a captured object, not a moon that formed alongside Neptune. Triton likely originated in the Kuiper Belt, that region of icy bodies beyond Neptune's orbit, and was captured by Neptune's gravity during a close encounter. The capture process would have been violent, placing Triton in a highly elliptical orbit. Triton is one of the coldest objects in the solar system, with surface temperatures around 38 Kelvin, only 38 degrees above absolute zero. Despite this extreme cold, Triton is geologically active. Voyager 2, during its 1989 flyby, discovered active geysers erupting from Triton's surface, shooting plumes of nitrogen gas and dark organic particles up to 8 kilometers high. These plumes are thought to be driven by solar heating. Even though Triton is far from the sun, sunlight can penetrate the translucent nitrogen ice that covers parts of the surface, warming the subsurface and causing nitrogen ice to sublimate into gas. The pressure builds until it erupts through weak points in the surface. The dark particles carried by the plumes settle back onto the surface, creating dark streaks that are visible in Voyager images. Triton's surface is young, with very few impact craters, suggesting that it has been resurfaced relatively recently, possibly by cryovolcanism or by nitrogen ice flows. The Moon has a tenuous atmosphere, mostly nitrogen, that extends several hundred kilometers above the surface. Triton's surface is a strange landscape of different terrain types. There are areas called cantaloupe terrain, where the surface is broken into a pattern of pits and ridges that resemble the skin of a cantaloupe. This terrain might have formed through diapirism, where warm, less dense ice rose through colder, denser ice, creating the pitted appearance. There are smooth plains, possibly frozen lakes of liquid nitrogen, or water that erupted onto the surface and then froze. There are ridges and troughs, evidence of tectonic activity, and there's a bright southern polar cap made of frozen nitrogen and methane that changes with the seasons. Triton's geology is complex and not fully understood, but it's clear that this moon has been shaped by a variety of processes, from impacts to cryovolcanism to sublimation and deposition of volatile ices. Triton is slowly spiraling inward toward Neptune due to tidal interactions. In a few billion years, it will cross Neptune's Roche limit and be torn apart by tidal forces, creating a spectacular ring system around the planet. Neptune's other moons are much smaller than Triton and fall into two groups: inner regular moons and outer irregular moons. The inner moons, including Naiad, Thalassa, Despina, Galatea, Larissa, and Proteus, orbit close to Neptune and are thought to have formed from the debris left over after Triton's capture. Triton's capture would have disrupted Neptune's original moon system, causing collisions that shattered any pre-existing moons. The current inner moons are the descendants of that debris, small, dark, irregularly shaped bodies. Mars has two small moons, Phobos and Deimos, both discovered in 1877 by astronomer Asaph Hall. These moons are tiny compared to the moons of the giant planets. Phobos is about 22 kilometers across at its widest, and Deimos is about 12 kilometers across. Both are irregularly shaped, more like potatoes than spheres, and both are heavily cratered. Their surfaces are dark, similar to carbonaceous asteroids, and their densities are low, suggesting they're porous. For many years, it was thought that Phobos and Deimos were captured asteroids, gravitationally captured by Mars from the nearby asteroid belt. But their orbits are nearly circular and lie almost exactly in Mars's equatorial plane, which is unusual for captured objects. Recent research suggests they might have formed from debris ejected into orbit around Mars by a massive impact, similar to how Earth's moon formed. Whatever their origin, Phobos and Deimos are the small, dark companions of the red planet, orbiting close to Mars and visible in the Martian sky. Phobos orbits Mars at a distance of only about 6,000 kilometers from the planet's surface, closer than any other known moon orbits its planet. This close orbit means that Phobos completes an orbit in just 7 hours and 39 minutes, faster than Mars rotates. From the Martian surface, Phobos would appear to rise in the west and set in the east, crossing the sky in about 4 hours. Phobos is slowly spiraling inward toward Mars due to tidal interactions. Mars's gravity creates tidal bulges in Phobos, and the friction from these bulges dissipates energy, causing the orbit to decay. In about 50 million years, Phobos will either crash into Mars or, more likely, be torn apart by tidal forces when it crosses Mars's Roche limit, creating a ring system around the planet. Phobos's surface is marked by grooves, long parallel channels that might be fractures caused by tidal stresses or by the impact that created the large crater Stickney, which is about 9 kilometers across, nearly half the diameter of Phobos itself. Deimos orbits farther from Mars than Phobos, at a distance of about 23,000 kilometers. Its orbital period is about 30 hours, slightly longer than a Martian day. From the Martian surface, Deimos would appear as a slow-moving point of light, taking about 2.5 days to cross the sky from east to west. Deimos is less heavily cratered than Phobos, and its surface appears smoother, possibly because it's covered with a thicker layer of regolith, fine dust created by micrometeorite impacts over billions of years. This regolith fills in craters and gives the Moon a softer appearance. Unlike Phobos, Deimos is slowly moving away from Mars, though the rate is very slow. Both Phobos and Deimos have been visited by spacecraft, and there are proposals for future missions to land on Phobos and return samples to Earth. These small moons might preserve material from the early solar system, and studying them could provide insights into the formation of Mars and the inner solar system. Pluto, reclassified as a dwarf planet in 2006, has 5 known moons, the largest of which is Charon. Charon is so large relative to Pluto, about half Pluto's diameter and 1/8 its mass, that the two bodies are sometimes considered a binary system rather than a planet and moon. The center of mass around which they orbit, called the barycenter, lies in the space between them rather than inside Pluto. Charon and Pluto are tidally locked not just in Charon's rotation. Charon always shows the same face to Pluto, but in both their rotations. Pluto also always shows the same face to Charon. They orbit their common center of mass every 6.4 days, and both rotate with the same period, so from Pluto's surface, Charon would appear to hang motionless in the sky, never rising or setting. From Charon, Pluto would do the same. This mutual tidal locking is unique in the solar system. The New Horizons spacecraft, which flew past Pluto in 2015, revealed Charon to be a world of surprising complexity, with a reddish polar cap, vast canyons, and a surface that tells a story of ancient geological activity. Charon's surface is divided into 2 main regions: a darker, more heavily cratered northern hemisphere, and a smoother, lighter southern hemisphere. The boundary between these regions is marked by a vast system of canyons and cliffs, some stretching over 1,000 kilometers and dropping as much as 9 kilometers. These canyons might have formed when Charon's interior froze and expanded, cracking the surface. The reddish color of Charon's north polar region, called Mordor Macula, is thought to be caused by organic molecules called tholins. These tholins are created when methane from Pluto's atmosphere escapes and is captured by Charon's weak gravity. Ultraviolet radiation from the sun then breaks down the methane, creating complex organic molecules that settle onto Charon's surface, particularly at the cold polar regions where they're trapped. Charon has no atmosphere and no geological activity today, but its surface preserves evidence of a dynamic past, of a time when its interior was warm enough to drive tectonic processes that reshaped the moon. Pluto's 4 smaller moons, Styx, Nix, Kerberos, and Hydra, are tiny, irregularly shaped bodies, ranging from about 10 to 50 kilometers across. They orbit Pluto and Charon in nearly circular orbits that lie in the same plane, suggesting they all formed from the same event. The leading theory is that these moons are debris from a massive impact between Pluto and another Kuiper Belt object early in the solar system's history. This impact would have created Charon and scattered debris into orbit, which then coalesced into the smaller moons. These tiny moons have surprisingly bright surfaces, reflecting much more light than Charon, suggesting they're covered in relatively clean water ice. They also have chaotic rotations, tumbling unpredictably rather than being tidally locked. This chaotic rotation is caused by the complex gravitational environment created by Pluto and Charon, whose combined gravitational field is irregular because of their binary nature. The small moons are constantly being tugged in different directions, preventing them from settling into stable rotational states. Eris, one of the largest known dwarf planets in the Kuiper Belt, has one known moon, Dysnomia. Dysnomia is much smaller than Eris, about 700 kilometers in diameter compared to Eris's 2,326 kilometers, but it's still a substantial moon. Dysnomia orbits Eris every 16 days at a distance of about 37,000 kilometers. The moon's discovery in 2005 was crucial for determining Eris's mass, which turned out to be slightly more massive than Pluto, one of the factors that led to the reclassification of Pluto as a dwarf planet. Dysnomia is thought to have formed from a collision, similar to how Charon formed around Pluto. The Kuiper Belt, that distant region beyond Neptune, is a realm of collisions and impacts, and many of the dwarf planets there likely have moons created by these violent events. Dysnomia's surface composition is unknown. We've never seen it up close, but it's likely similar to Eris, covered in methane ice and other frozen volatiles. Haumea, another large Kuiper Belt object, is one of the strangest bodies in the solar system. It's shaped like an elongated ellipsoid, spinning so rapidly that it completes a rotation every 4 hours. This rapid rotation has stretched Haumea into a football shape with dimensions of roughly 2,000 by 1,500 by 1,000 kilometers. Haumea has 2 known moons, Hyakka and Namaka, and a ring system, making it the first Kuiper Belt object known to have rings. The moons are thought to be fragments from a massive impact that occurred billions of years ago, an impact so violent that it stripped away Haumea's outer ice mantle, leaving behind a dense rocky core and scattering debris into orbit. Some of this debris became the moons, and some formed the ring. Hyakka, the larger moon, is about 310 kilometers across and orbits Haumea every 49 days. Namaka is smaller, about 170 kilometers across, and orbits every 18 days. Both moons are covered in water ice, likely material from Haumea's original ice mantle. The formation of moons is a story of violence and chance. Some moons, like Earth's moon and Charon, formed from massive impacts that ejected material into orbit. Others, like the Galilean moons and Saturn's major moons, formed from the disk of gas and dust that surrounded the giant planets as they were forming, a process similar to how planets form around stars. Still others, like Triton and many of the irregular moons of the giant planets, are captured objects, asteroids or Kuiper Belt objects, that wandered too close and were gravitationally captured. Each formation mechanism leaves its signature. Moons formed from impacts tend to be large relative to their parent body and have compositions similar to the parent. Moons formed from circumplanetary disks tend to orbit in the planet's equatorial plane, in circular orbits. Captured moons tend to have inclined, eccentric, and sometimes retrograde orbits. By studying the orbits, compositions, and characteristics of moons, we can piece together the violent and chaotic history of the early solar system. Tidal forces play a crucial role in the evolution of moons. When a moon orbits close to a planet, the planet's gravity pulls more strongly on the near side of the moon than the far side, creating a tidal bulge. If the moon is rotating faster than it orbits, this bulge is dragged ahead of the line connecting the planet and moon, and the planet's gravity pulls back on the bulge, slowing the moon's rotation. Over time, this process leads to tidal locking, where the moon's rotation period equals its orbital period. Most large moons in the solar system are tidally locked to their planets. Orbital resonances are another powerful force shaping moon systems. A resonance occurs when 2 or more moons have orbital periods that are related by a simple ratio, like 2, 1, or 3, 2. These resonances can be stable, maintaining themselves over billions of years, or they can be unstable, leading to chaotic orbital evolution. The Laplace resonance of Io, Europa, and Ganymede is a stable resonance that maintains the orbital eccentricities of Io and Europa, driving tidal heating. Saturn's moons show many resonances. Mimas and Tethys are in a 4, 2 resonance, and Dione are in a 2, 1 resonance, and Titan and Hyperion are in a 4-3 resonance. These resonances affect the moon's orbit and can drive geological activity through tidal heating. Resonances can also clear gaps in ring systems, as shepherd moons gravitationally interact with ring particles in resonant orbits. The solar system is full of these gravitational harmonies, invisible but powerful forces that have shaped the architecture of planetary systems. The diversity of moons in our solar system is staggering. There are volcanic moons like Io, ocean moons like Europa and Enceladus, moons with thick atmospheres like Titan, captured asteroids like Phobos and Deimos, and ancient cratered worlds like Callisto and Umbriel. There are moons larger than planets, and moons barely larger than mountains. There are moons that orbit in hours, and moons that take years to complete an orbit. This diversity reflects the diversity of processes that create and shape moons: impacts, accretion, capture, tidal heating, cryovolcanism, and more. Each moon is a natural experiment, showing us what happens under different conditions of size, composition, distance from the sun, and gravitational environment. By studying this diversity, we learn not just about individual moons, but about the fundamental processes that shape all worlds, including Earth. The moons of the solar system are a laboratory for planetary science, offering insights we couldn't gain from studying planets alone. Some moons might harbor life. Europa, Enceladus, and Titan are considered the most promising candidates. Europa and Enceladus both have subsurface oceans in contact with rocky seafloors, where hydrothermal vents might provide chemical energy for life. Enceladus is actively venting its ocean into space, and future missions might be able to sample this material for biosignatures without even landing. Titan has a different kind of potential habitability. Its surface lakes of liquid methane and ethane, combined with complex organic chemistry in its atmosphere, create an environment where exotic forms of life, based on different chemistry than Earth life, might exist. There's also the possibility of life in Titan's subsurface water ocean. The search for life beyond Earth increasingly focuses on moons rather than planets. Moons can have habitable environments even in the outer solar system, far from the sun, as long as they have internal heat sources like tidal heating or radioactive decay. The discovery of life on a moon would be one of the most profound discoveries in human history. The study of moons has been revolutionized by spacecraft missions. Voyager 1 and 2, launched in 1977, provided our first close-up views of the moons of Jupiter, Saturn, Uranus, and Neptune, revealing worlds of unexpected complexity. The Galileo mission orbited Jupiter from 1995 to 2003, studying the Galilean moons in detail and providing evidence for Europa's subsurface ocean. The Cassini mission orbited Saturn from 2004 to 2017, discovering Enceladus's plumes, studying Titan's atmosphere and surface, and observing the intricate interactions between Saturn's moons and rings. New Horizons flew past Pluto in 2015, revealing Charon and Pluto's small moons. Future missions are planned to return to these worlds. NASA's Europa Clipper will conduct detailed studies of Europa's ice shell and ocean. The ESA's JUICE mission we'll study Jupiter's icy moons, particularly Ganymede. There are proposals for missions to Enceladus, Titan, and Triton. Each mission reveals new mysteries and raises new questions, driving our understanding of these distant worlds. Exomoons, moons, orbiting planets around other stars, are the next frontier. We've discovered thousands of exoplanets, and it's reasonable to assume that many of them have moons. But detecting exomoons is extraordinarily difficult. Moons are small and don't produce their own light, so we can't see them directly. We have to infer their presence from subtle effects on the light from the star or on the planet's motion. Several candidate exomoons have been proposed, but none have been confirmed. The most promising candidates are large moons, perhaps the size of Neptune, orbiting giant planets. If such moons exist, they might be habitable even if they orbit far from their star. If they have substantial atmospheres and tidal heating, the detection of the first confirmed exomoon will open a new chapter in astronomy, revealing whether the moon systems we see in our solar system are common or rare, and expanding the number of potentially habitable worlds in the galaxy. Moons are not static. They're evolving, shaped by ongoing processes. Io's surface is constantly renewed by volcanic eruptions. Europa's ice shell is cracking and reforming. Enceladus is venting its ocean into space. Our moon is slowly drifting away from Earth. Phobos is spiraling toward Mars. Triton is spiraling toward Neptune. These are not frozen, unchanging worlds, but dynamic systems, responding to gravitational forces, internal heat, and the slow passage of time. Over billions of years, moon systems change. Moons can be destroyed by tidal forces or impacts. New moons can form from debris. Orbits shift and evolve. The moon systems we see today are snapshots of an ongoing process, a process that began with the formation of the solar system and will continue until the sun dies. Moons are reminders that the universe is not static, but constantly changing, that everything we see is part of a vast, slow dance of gravity and time. Humans have walked on a moon. Between 1969 and 1972, 12 astronauts from the Apollo program set foot on the lunar surface, the only humans to have ever stood on another world. They collected 382 kilograms of lunar rocks and soil, conducted experiments, took photographs, and left behind equipment that's still on the moon today. The Apollo missions were driven by Cold War competition, but they were also expressions of human curiosity and ambition, our desire to explore and understand the universe. The images of Earth rising over the lunar horizon, a blue and white marble against the black of space, changed how we see our planet. They showed us Earth as a fragile oasis, a single world in the vastness of space. No human has returned to the moon since 1972, but there are plans to go back. NASA's Artemis program aims to land astronauts on the moon in the coming years, this time to stay, establishing a permanent presence that will serve as a stepping stone to Mars and beyond. The moon has been a presence in human culture for as long as there have been humans. Ancient peoples tracked the moon's phases, using them to mark time and create calendars. The lunar cycle, about 29.5 days from new moon to new moon, became the basis for months in many calendar systems. The moon appears in mythology and religion across cultures. In ancient Greece, the moon was associated with the goddess Artemis. In ancient Rome, with Luna. In Hindu mythology, with Chandra. In Chinese culture, the moon is central to the Mid-Autumn Festival. The moon has been seen as a symbol of femininity, of cycles and change, of mystery and madness. The word lunatic comes from the Latin luna, reflecting the ancient belief that the moon could affect the mind. The moon has inspired countless works of art, literature, and music. It's a universal symbol, recognized and revered by cultures around the world, a constant presence that connects us to our ancestors, who looked up at the same moon thousands of years ago. Before telescopes, people could see only 5 moons with the naked eye: our moon and the 4 Galilean moons of Jupiter, though the Galilean moons appear as points of light near Jupiter and were not recognized as moons until Galileo observed them with his telescope. Our moon is the only celestial body other than the sun that's bright enough and large enough to show a visible disk to the naked eye. Ancient astronomers observed the moon's phases, its motion against the background stars, and the occasional lunar eclipse when Earth's shadow falls on the moon. They noticed that the moon always shows the same face, though they didn't understand why. They saw the dark patches, the Maria, and imagined different patterns: a face, a rabbit, a man carrying sticks. The invention of the telescope in the early 1600s revolutionized lunar observation. Galileo was one of the first to point a telescope at the moon, and he saw mountains, craters, and valleys, proving that the moon was a world with topography, not a perfect sphere, as Aristotelian philosophy had claimed. The far side of the moon remained a mystery until the space age. Because the moon is tidally locked to Earth, the same hemisphere always faces us, and the far side is forever hidden from view. People speculated about what might be on the far side. Some imagined it might be radically different, perhaps harboring an atmosphere, or even life. In 1959, the Soviet Luna 3 spacecraft flew around the moon and took the first photographs of the far side, revealing a landscape similar to the near side, but with fewer Maria and more craters. The far side remained largely unexplored until more recent missions. In 2019, China's Chang'e 4 mission became the first spacecraft to land on the far side, deploying a rover to explore the surface. The far side is sometimes called the dark side, but this is a misnomer. It receives just as much sunlight as the near side. It's dark only in the sense that it's hidden from Earth, a hemisphere we couldn't see until we developed the technology to send spacecraft beyond our planet. Lunar eclipses occur when Earth passes between the sun and the moon, casting its shadow on the lunar surface. During a total lunar eclipse, the moon doesn't disappear completely, but takes on a reddish color, often called a blood moon. This red color is caused by sunlight passing through Earth's atmosphere and being refracted onto the moon. Earth's atmosphere scatters blue light and allows red light to pass through, the same process that makes sunsets red. This red light illuminates the moon during the eclipse. Lunar eclipses can only occur during a full moon, when the sun, Earth, and moon are aligned. They don't happen every month, because the moon's orbit is tilted about 5 degrees relative to Earth's orbit around the sun, so the alignment is usually not exact. Lunar eclipses are visible from anywhere on Earth where the moon is above the horizon, and they can last for several hours. Ancient peoples often feared eclipses, seeing them as omens or signs of divine displeasure, but they also used them to refine their understanding of celestial mechanics. The moon affects Earth in ways beyond tides. It stabilizes Earth's axial tilt, preventing wild swings in climate that would make complex life difficult. It creates tidal friction that slows Earth's rotation, lengthening our days. It provides light at night, which has shaped the evolution of nocturnal animals and influenced human behavior and culture. Some studies suggest that the moon's gravitational pull might trigger earthquakes when tidal stresses add to existing geological stresses, though this is debated. The moon's presence has shaped Earth's history in profound ways. The tidal pools created by lunar tides might have been important environments for the origin of life. The regular cycle of the moon's phases provided early humans with a natural calendar, helping them track seasons and plan agricultural activities. The moon has been a guide for navigation, a source of inspiration for poetry and art, and a symbol of the unreachable that eventually became reachable when humans landed on its surface. Earth without the moon would be a very different world, and life on Earth might never have evolved the way it did. Amateur astronomers have contributed significantly to our understanding of moons. With modest telescopes, amateurs can observe the moons of Jupiter and Saturn, track their positions, and even observe phenomena like mutual eclipses when one moon passes in front of another. Amateur astronomers have discovered comets that later impacted Jupiter, observed storms on Saturn, and contributed to long-term monitoring programs that track changes in planetary atmospheres and moon orbits. The accessibility of moons to amateur observation makes them a gateway to planetary science. Anyone with a small telescope can see the Galilean moons, watch them change positions from night to night, and experience the same sense of wonder that Galileo felt over 400 years ago. Amateur observations complement professional research, providing data over long time periods and catching transient events that might be missed by professional observatories. The study of moons is not just for scientists with access to spacecraft and large telescopes. It's for anyone who looks up at the night sky with curiosity and a desire to understand the worlds beyond our own. The naming of moons reflects both scientific tradition and cultural heritage. Earth's moon is simply called the moon, from the Old English mona. The moons of other planets are named after figures from mythology. Jupiter's moons are named after lovers and descendants of the god Jupiter, Zeus in Greek mythology. Saturn's moons are named after Titans and other figures from Greek and Roman mythology. Uranus's moons are uniquely named after characters from Shakespeare and Alexander Pope. Neptune's moons are named after Greek and Roman water deities. The naming conventions are established by the International Astronomical Union, which approves names proposed by discoverers. As we discover more moons, particularly small, irregular moons around the giant planets, we're running out of suitable mythological names. Some recently discovered moons have been given provisional designations and await formal names. The names we give to moons reflect our cultural heritage, connecting the scientific endeavor of exploring the solar system with the ancient stories and myths that have shaped human culture for millennia. The study of moons has practical applications beyond pure science. Understanding tidal forces helps us predict ocean tides on Earth, which is crucial for navigation, coastal management, and marine ecosystems. Studying the geology of moons helps us understand geological processes on Earth, particularly cryovolcanism and ice tectonics that might occur in Earth's polar regions or in subsurface environments. The search for life on moons like Europa and Enceladus drives the development of new technologies for detecting biosignatures and exploring extreme environments, technologies that have applications on Earth. The challenges of sending spacecraft to distant moons and operating in harsh radiation environments drive innovations in engineering, material science, and robotics. The study of exomoons will help us understand planetary system formation and identify potentially habitable worlds beyond our solar system. The knowledge we gain from studying moons enriches our understanding of our place in the universe and inspires new generations of scientists, engineers, and explorers. The moon has been a target for commercial ventures. Several private companies are developing lunar landers and rovers, aiming to deliver payloads to the moon for scientific research, resource prospecting, and even tourism. There's interest in mining the moon for resources like water ice, which could be used to produce rocket fuel and rare earth elements. Some envision establishing permanent lunar bases that would serve as research stations, manufacturing facilities, or waypoints for missions to Mars. The Moon's low gravity and lack of atmosphere make it an ideal location for certain types of manufacturing and for launching spacecraft to other destinations. The 1967 Outer Space Treaty establishes that no nation can claim sovereignty over the Moon, but it doesn't prohibit commercial activities. As technology advances and the cost of space access decreases, the Moon is transitioning from a destination for government-funded exploration to a potential site for commercial activity. Whether this is desirable and how to manage lunar resources sustainably are questions that humanity will need to address in the coming decades. The moons of the solar system are time capsules, preserving records of the early solar system. Moons with old, heavily cratered surfaces like Callisto and Umbriel show us what the solar system looked like billions of years ago, when impacts were frequent and violent. Moons with young surfaces like Io and Europa show us that geological processes are still active, that the solar system is not a static place but constantly changing. The composition of moons tells us about the materials that were available in different regions of the solar system when they formed. The icy moons of the outer solar system are rich in water and organic compounds, materials that were too volatile to condense in the inner solar system where Earth formed. By studying moons, we learn about the conditions that existed when the solar system was young, about the processes that shaped planets and moons, and about the distribution of materials that made life on Earth possible. Looking at moons reminds us of the vastness and diversity of the universe. Each moon is a world with its own story, its own geology, its own mysteries. Some are volcanic, some are icy, some have atmospheres, some have oceans. Some are geologically active, some are ancient and unchanging. They orbit planets of different sizes and compositions, at different distances from the Sun, in different gravitational environments. This diversity shows us that the universe is full of possibilities, that worlds can exist in forms we never imagined. It challenges our assumptions about what's normal or typical. It expands our sense of what's possible. And it reminds us that Earth, for all its uniqueness, is part of a larger cosmic story, a story of gravity and time, of formation and evolution, of worlds orbiting worlds in the darkness of space. The moons of the solar system are our neighbors, our companions on this journey through the cosmos, silent witnesses to the slow unfolding of cosmic time. Despite decades of study, many mysteries about moons remain unsolved. We don't know exactly how Earth's moon formed. The giant impact hypothesis is the leading theory, but the details are uncertain. How did the impactor, Theia, end up on a collision course with Earth? Why is the moon's composition so similar to Earth's mantle? How did the debris disk coalesce into a single moon rather than multiple moons? Computer simulations can reproduce some aspects of the moon's formation, but not all. There are competing theories and ongoing debates. Similarly, we don't fully understand the internal structure of many moons. Do Europa and Enceladus have single global oceans, or multiple isolated pockets of liquid water? The origin of Phobos and Deimos remains uncertain. Are they captured asteroids, as their dark surfaces and low densities suggest? Or did they form from debris ejected by a massive impact on Mars, as their nearly circular equatorial orbits suggest? Recent research favors the impact hypothesis, but the evidence is not conclusive. Similarly, the origin of Saturn's rings is debated. Are they ancient, formed at the same time as Saturn, or are they young, perhaps only a few 100 million years old? created when a moon or comet was torn apart by tidal force. We don't fully understand the source of Enceladus's heat. Tidal heating from its orbital resonance with Dione should provide some heat, but calculations suggest it's not enough to maintain a global ocean and power the observed geological activity. There must be additional heat sources or mechanisms that make tidal heating more efficient. Perhaps the ocean is in contact with a porous, rocky core that allows for more efficient heat transfer. Perhaps there are chemical reactions occurring in the ocean, or at the ocean-rock interface that release heat. Perhaps the ice shell has unusual properties that affect heat flow. We won't know until we send a mission to study Enceladus in detail, perhaps landing on the surface or flying through the plumes to sample the ocean material directly. The mystery of Enceladus's heat is not just a curiosity, it's central to understanding whether the moon could harbor life. The nature of Titan's lakes and seas is not fully understood. We know they're filled with liquid methane and ethane, but we don't know how deep they are or what lies beneath them. Are they shallow puddles, or are they deep bodies of liquid? Do they have currents and waves? Are there tides driven by Saturn's gravity? The Cassini mission's radar observations provided some information, but many questions remain. There's also the mystery of Titan's methane. Methane in Titan's atmosphere is broken down by sunlight, so it should disappear over millions of years. Yet Titan has a thick methane atmosphere. There must be a source replenishing the methane. Is it cryovolcanism, with methane erupting from the interior? Is it a subsurface reservoir of methane that slowly leaks into the atmosphere? Or is there some other process we haven't considered? Understanding Titan's methane cycle is key to understanding the moon's climate and surface processes. Miranda's bizarre surface remains a puzzle. Why does this small moon have such diverse terrain, with old cratered regions next to young grooved regions? Was Miranda shattered by an impact and then reassembled? Was it heated by tidal forces when it was in an orbital resonance? Or is there some other explanation? The Voyager 2 flyby in 1986 provided our only close-up images of Miranda, and they raised more questions than they answered. Similarly, Iapetus's equatorial ridge is a mystery. This mountain range, up to 20 kilometers high, circles most of the moon's equator. How did it form? Is it material that fell back onto Iapetus from a destroyed ring? Is it the result of ancient tectonic activity? Is it related to Iapetus's unusual shape? We don't know. These features are so strange that they challenge our understanding of how small, icy moons evolve. The possibility of life on moons is one of the most profound mysteries. Europa, Enceladus, and Titan all have environments that might be habitable, but we don't know if they actually harbor life. The subsurface oceans of Europa and Enceladus could have the right conditions: liquid water, chemical energy from hydrothermal vents, and organic compounds. But does life exist there? If it does, what form does it take? Is it simple, single-celled organisms, or could it be more complex? How would it survive in the dark, cold ocean, isolated from sunlight? Titan presents a different question. Could life exist in its methane lakes, using a completely different biochemistry than Earth life? These are questions we can't answer from Earth. We need to send missions to these moons, to sample their oceans and atmospheres, to search for biosignatures. The discovery of life on a moon would be one of the most important discoveries in human history, fundamentally changing our understanding of our place in the universe. The future of moon exploration is bright. NASA's Europa Clipper mission, scheduled to launch in the 2002, will conduct detailed studies of Europa's ice shell, ocean, and potential habitability. It will fly by Europa multiple times, using radar to probe the ice shell, spectrometers to analyze surface composition, and magnetometers to study the ocean. The European Space Agency's JUICE mission will study Jupiter's icy moons, with a focus on Ganymede, where it will eventually enter orbit. There are proposals for missions to Enceladus to fly through its plumes and sample the ocean material, and to Titan to explore its lakes and seas with boats or submarines. There are plans to return to the Moon, with NASA's Artemis program aiming to establish a permanent human presence. China, India, and private companies are also developing lunar missions. The coming decades will see an unprecedented exploration of moons, revealing secrets that have been hidden for billions of years. The search for exomoons is just beginning. As our telescopes and detection methods improve, we'll likely discover moons orbiting planets around other stars. These exomoons could be common, perhaps as common as exoplanets. Some might be habitable, with atmospheres and liquid water on their surfaces or in subsurface oceans. The detection of an exomoon would open new possibilities for finding life beyond our solar system. Moons orbiting giant planets in the habitable zone of their star could be warm enough for liquid water, even if the planet itself is a gas giant unsuitable for life. Moons with substantial atmospheres and tidal heating could be habitable even far from their star. The universe might be full of habitable moons, worlds we haven't even begun to explore. The first confirmed detection of an exomoon will be a milestone in astronomy, expanding our understanding of planetary systems and the potential for life in the universe. The long-term fate of moons is written in the laws of gravity. Phobos will spiral into Mars and either crash into the surface or be torn apart by tidal forces, creating a ring system. Triton will spiral into Neptune and meet a similar fate. Our moon will continue to drift away from Earth, eventually becoming so distant that total solar eclipses will no longer occur, as the moon will appear too small to cover the sun. These processes take millions or billions of years, but they're inevitable. Moons are not permanent features of the solar system. They're born, they evolve, and eventually they're destroyed or transformed. The moon systems we see today are temporary configurations, snapshots of an ongoing process. In the distant future, the solar system will look different. Some moons will be gone, new moons might form from debris, and the orbits of surviving moons will have changed. Everything is in motion. Everything is evolving, driven by the relentless pull of gravity. Moons teach us about resilience and adaptation. Life on Earth has adapted to the moon's influence, to the tides it creates, to the light it provides at night, to the regular cycle of its phases. If life exists on Europa or Enceladus, it has adapted to environments radically different from Earth. Dark, cold oceans beneath kilometers of ice, with no sunlight, relying on chemical energy from hydrothermal vents. If life exists on Titan, it has adapted to liquid methane instead of water, to temperatures where water is as hard as rock. These hypothetical forms of life, if they exist, show us that life can adapt to almost any environment, that the conditions we consider essential might not be universal. This expands our sense of where to look for life and what forms it might take. It suggests that the universe might be full of life, in forms we can barely imagine, thriving in environments we would consider hostile. The study of moons is a collaborative endeavor. Scientists from around the world work together, sharing data from telescopes and spacecraft, developing theories, testing hypotheses. Space agencies collaborate on missions, with NASA, ESA, JAXA, and others pooling resources and expertise. Amateur astronomers contribute observations. The knowledge we gain about moons is not the property of any one nation or institution. but part of humanity's collective understanding of the universe. This collaboration reflects the universal appeal of exploration, the shared curiosity that drives us to understand the worlds beyond our own. Moons belong to everyone. They're part of our common heritage, objects of wonder and study that unite us in our quest to understand the cosmos. The exploration of moons is a human endeavor, transcending borders and bringing us together in pursuit of knowledge. Moons inspire us. They inspire scientists to develop new theories and technologies, to push the boundaries of what's possible. They inspire engineers to design spacecraft that can survive the harsh environments of the outer solar system, to develop instruments that can detect the faint signatures of subsurface oceans or atmospheric biosignatures. They inspire artists and writers to imagine what these worlds might be like, to create stories of exploration and discovery. They inspire all of us to look up at the night sky and wonder, what's out there? What secrets do these distant worlds hold? Could there be life on Europa or Enceladus? What would it be like to stand on Titan and watch methane rain fall into a methane sea? These questions drive us forward, fueling our curiosity and our desire to explore. Moons remind us that the universe is vast and full of wonders, that there's always more to discover, always new frontiers to explore. In the end, moons are reminders of connection. They're connected to their planets by gravity, locked in orbital dances that have continued for billions of years. They're connected to each other through resonances and tidal interactions. They're connected to the history of the solar system, preserving records of ancient impacts and geological processes. And they're connected to us. Our moon shapes Earth's tides and stabilizes our climate. The moons of other planets teach us about planetary science and the potential for life. The study of moons connects scientists across disciplines and across nations, and moons connect us to the cosmos, reminding us that we're part of something larger, a universe of worlds orbiting worlds, all governed by the same physical laws, all part of the same cosmic story. As you drift towards sleep tonight, think of the moons, silent and patient, orbiting in the darkness, waiting to reveal their secrets. Every moon in the solar system is unique, yet they all share something fundamental. They're all bound by gravity to larger worlds, orbiting in the darkness, shaped by forces beyond their control. Some moons are active, volcanic, or geologically dynamic, constantly changing. Others are ancient and quiet, their surfaces unchanged for billions of years. Some have atmospheres, some have oceans, some are bare rock or ice. But all of them are worlds, with their own histories, their own stories written in craters and canyons, in ice and rock. When you look at Jupiter through a telescope and see the 4 Galilean moons arranged like pearls on a string, you're seeing 4 distinct worlds, each as complex as any planet. When you look at our moon, you're seeing a companion that has been with Earth for over 4 billion years, shaping our world and being shaped by it. Every moon is a reminder that the universe is not empty, but full of worlds, each one worthy of study and wonder. The colors of moons tell stories. Io is yellow and orange and red, colored by sulfur compounds from its volcanoes. Europa is white and tan, its surface covered in relatively clean water ice crisscrossed with reddish-brown streaks. Ganymede has dark and light regions, ancient cratered terrain next to younger grooved terrain. Callisto is dark and heavily cratered, one of the oldest surfaces in the solar system. Titan appears orange through its thick atmosphere, colored by organic haze. Enceladus is brilliant white, its surface constantly renewed by fresh ice from its plumes. Iapetus is two-toned, one hemisphere bright, and one dark. Our moon is grey, its surface covered in regolith pulverized by billions of years of impacts. These colors are not just aesthetic. They tell us about composition, about geological processes, about age and activity. They're clues to understanding these worlds, written in wavelengths of light that travel across the solar system to reach our telescopes. The sounds of moons are silent. There's no air on most moons to carry sound waves, so even the most violent events, volcanic eruptions on Io, geysers on Enceladus, impacts that create craters, all happen in complete silence. On Titan, with its thick atmosphere, sound could travel, but it would sound different than on Earth. The atmosphere is denser and the gravity is lower, so sound waves would travel differently. Your voice would be deeper and sounds would carry farther. But for most moons, there's only silence. The universe is quieter than we imagine. All the drama of moon formation, of tidal heating, of orbital evolution, happens without sound. It's a visual universe, a universe of light and gravity and motion, but not of sound. This silence is part of the peace of contemplating moons. They orbit in quietness, patient and eternal, undisturbed by noise. The gravity on moons varies dramatically. On Ganymede, the largest moon, gravity is about 15% of Earth's. You could jump about 6 times higher than on Earth. On our moon, gravity is about 17% of Earth's, which is why Apollo astronauts could hop and bound across the surface. On smaller moons like Phobos or Deimos, gravity is so weak that you could easily jump into orbit if you weren't careful. On Titan, despite being smaller than Ganymede, the thick atmosphere creates air resistance that would make movement feel different, almost like moving underwater. These differences in gravity would make each moon feel unique. The way you move, the way objects fall, the way dust settles, all would be different. Gravity shapes not just the geology of moons, but the experience of being on them. It's one of the fundamental forces that makes each world distinct, that gives each moon its own character. The view from a moon would be spectacular. From our moon, Earth hangs in the sky, about 4 times larger than the moon appears from Earth, showing phases as the moon does, waxing and waning over the course of a month. From Io, Jupiter would dominate the sky, a massive disk showing bands of clouds and the Great Red Spot. From Europa, you would see Jupiter too, and you might see Io passing in front of the planet, a tiny dark disk transiting the giant world. From Titan, you wouldn't see much through the thick orange haze, but if you could get above the atmosphere, you would see Saturn with its magnificent rings. From Triton, Neptune would appear as a blue disk, and you would see the Sun as a bright but distant star. Each moon offers a different perspective, a different view of the solar system. The temperatures on moons range from the extreme to the merely cold. Io's volcanic regions can reach temperatures of over 1,600 Kelvin, hot enough to melt rock. But most of Io's surface is frigid, around 110 Kelvin. Europa's surface is about 100 Kelvin, cold enough that water ice is as hard as granite. Titan's surface is around 94 Kelvin, cold enough for methane to be liquid. Triton, one of the coldest objects in the solar system, has surface temperatures around 38 Kelvin. Our moon experiences extreme temperature swings from about 400 Kelvin in direct sunlight to about 100 Kelvin in shadow, because there's no atmosphere to moderate temperatures. These temperatures are hostile to life as we know it, but beneath the surfaces of some moons, in subsurface oceans warmed by tidal heating, temperatures might be much more hospitable. The cold of the surface is not the whole story. Beneath the ice, There might be warmth, liquid water, and perhaps life. The age of moons varies. Some moons, like Callisto and Umbriel, have ancient surfaces that date back billions of years, nearly to the formation of the solar system. Other moons, like Io and Europa, have young surfaces, constantly renewed by geological activity. The surface of Io is only a few million years old on average, constantly buried under new volcanic deposits. Europa's surface is estimated to be 40 to 90 million years old, young by geological standards. Our moon's surface is a mix of ancient highlands, over 4 billion years old, and younger Maria, between 3 and 4 billion years old. The age of a surface tells us about geological activity. Young surfaces mean active processes, old surfaces mean geological quiescence. By studying the ages of moon surfaces, we can reconstruct the history of the solar system, understanding when impacts were common, when volcanism was active, when moons were geologically alive. The orbits of moons are not random but follow patterns determined by gravity and history. Most large moons orbit in their planet's equatorial plane, a consequence of forming from a disk of material around the planet. Captured moons often have inclined, eccentric, and sometimes retrograde orbits, reflecting their origin outside the planetary system. Moons in resonances have orbital periods related by simple ratios, locked together by gravitational interactions. Some moons have nearly circular orbits, others have eccentric orbits that bring them closer to and farther from their planet. These orbital characteristics are clues to understanding how moons formed and how they've evolved. They're the result of billions of years of gravitational interactions, of tidal forces, of resonances and perturbations. The orbits we see today are not the orbits that existed when the solar system was young. They've changed, evolved, and they'll continue to change in the future. Moons have been the subject of human imagination long before we understood what they were. Ancient peoples saw our moon and created myths to explain it. They saw patterns in the dark Maria and imagined faces, animals, and figures. They tracked the moon's phases and used them to create calendars and predict eclipses. They wondered about the other lights in the sky, the planets, not knowing that some of those planets had moons of their own. The invention of the telescope revealed those moons, and each discovery expanded our understanding of the solar system. Galileo's discovery of Jupiter's moons showed that not everything orbits Earth. Huygens's discovery of Titan showed that moons could be large worlds. Each new moon discovered added to our knowledge, challenged our assumptions, and expanded our sense of the cosmos. The history of moon discovery is a history of human curiosity, of our drive to understand the universe. The future might see humans living on moons. The moon is the most likely candidate, close enough to Earth for relatively quick travel, with resources like water ice that could support a permanent base. Lunar bases could serve as research stations, manufacturing facilities, or waypoints for missions to Mars and beyond. Some envision mining operations extracting resources from the moon. Others imagine tourism, with people traveling to the moon to experience low gravity and see Earth from space. Further in the future, we might establish outposts on other moons. Titan, with its thick atmosphere and abundant organic compounds, might be a site for research into prebiotic chemistry. Callisto, outside Jupiter's intense radiation belts, might be a base for exploring the Jupiter system. These are speculations, but they're based on real possibilities. As technology advances, moons might transition from objects of study to places where humans live and work. Every moon is a world waiting to be explored. We've sent spacecraft to many moons, but we've only scratched the surface. We've flown by, we've orbited, we've landed in a few cases, but there's so much more to learn. We haven't drilled through the ice of Europa to sample its ocean. We haven't explored the depths of Titan's methane seas. We haven't landed on Enceladus to study its plumes up close. We haven't returned samples from Phobos or Deimos. We haven't sent a mission to Uranus or Neptune in decades, and their moons remain largely mysterious. Each moon holds secrets, answers to questions about the solar system's formation, about geological processes, about the potential for life. The exploration of moons is a project that will take generations, a long-term endeavor that will reveal the diversity and wonder of these worlds. Every mission brings new discoveries, new questions, new reasons to keep exploring. As you lie here drifting towards sleep, the moons are still there, orbiting in the darkness. Our moon is making its slow circuit around Earth, pulling at the oceans, creating tides. The Galilean moons are orbiting Jupiter, Io erupting, Europa's ocean sloshing beneath its ice, Ganymede generating its magnetic field, Callisto preserving its ancient surface. Titan is experiencing its slow seasons, methane evaporating and condensing. Enceladus is venting its ocean into space. Triton is orbiting Neptune backward, slowly spiraling inward. Phobos is racing around Mars, doomed to fall. All across the solar system, moons are orbiting, patient and silent, governed by gravity, shaped by time. They've been there for billions of years, and they'll be there for billions more. There are companions in the cosmos, worlds that share this solar system with us. Each one a mystery, each one a wonder. Sleep well, knowing that the universe is full of these quiet worlds, orbiting in the darkness, waiting for us to discover their secrets. The moons are watching over the night, as they always have, as they always will.